Hey there, science fans! Today we're diving into the exciting world of nanocomposites materials that are shaking things up in a big way. Imagine taking something like plastic and giving it superpowers by adding tiny particles. That's nanocomposites in a nutshell. These tiny particles, called nanoparticles, are like secret ingredients that can completely change how a material behaves. Want something stronger, more flexible? How about better at conducting electricity? Nanoparticles can do it all. This means nanocomposites have the potential to revolutionize everything from electronics to medicine. We're talking about lighter, faster, and more efficient devices. And that's just the tip of the iceberg. So, buckle up, science explorers, as we explore the amazing world of radiation-enhanced nanocomposites and how they're shaping the future. Now let's talk polymers. You probably know them better as plastics, those versatile materials we use in almost everything. But polymers can be so much more when combined with nanoparticles. Enter polymeric nanocomposites, a special type of nanocomposite where polymers team up with nanoparticles to achieve incredible things. Think of it like this. The polymer is the foundation, providing structure and flexibility, while the nanoparticles are the superheroes, adding their unique abilities to the mix. Why does this matter? Well, polymeric nanocomposites have the potential to outperform traditional materials in countless ways. They can be stronger, lighter, more durable, and even conduct electricity better. This opens up a world of possibilities for creating cutting-edge technologies that can improve our lives. And the best part? We're only just scratching the surface of what these amazing materials can do. In our quest for better nanocomposites, scientists have been experimenting with different materials. One promising combination is polyvinyl alcohol, or PVA, and multi-walled carbon nanotubes, or MWCNTs. PVA is a popular polymer known for its flexibility and strength. It's like the reliable friend who's always there for you. MWCNTs, on the other hand, are tiny cylinders of carbon atoms with remarkable electrical conductivity. Think of them as the super-fast messengers, zipping electrons around with ease. But wait, there's more! By adding a touch of nitrogen to the MWCNTs, we create MWCNT-NH₂. This nitrogen boost enhances the interaction between the MWCNTs and PVA, leading to even better performance. So there you have it, PVA, MWCNTs, and a sprinkle of nitrogen, the dream team for creating high-performing nanocomposites. Now, let's talk about how we can take these nanocomposites to the next level using radiation. It might sound counterintuitive, but exposing materials to gamma and ion beams can actually improve their properties. Think of it like this. The radiation acts like a tiny sculptor, rearranging the atoms within the nanocomposite to create a more efficient structure. This can lead to increased electrical conductivity, meaning the material can carry electricity even better. But that's not all. Radiation can also improve the stability of the nanocomposite, making it more resistant to heat and other environmental factors. This is crucial for creating devices that can withstand the test of time. So by harnessing the power of radiation, we can unlock the full potential of these amazing materials. The enhanced properties of radiation-treated nanocomposites open up a world of possibilities in various fields, particularly in electronics and medicine. Imagine flexible and transparent electronics, super-efficient solar cells, and even advanced sensors for medical diagnostics. These are just a few examples of how these materials can revolutionize our lives. And the best part? This technology has the potential to benefit everyone, especially in developing countries like Egypt. By investing in research and development, we can create new industries, boost the economy, and improve the lives of millions. So, there you have it. Radiation-enhanced nanocomposites, a shining example of how science and innovation can create a brighter future for all. Hey tech enthusiasts, welcome back to the channel. Today, I'm diving into something truly next-gen, how radiation can supercharge nanocomposites. Trust me, this is a game changer. Alright, imagine this. Scientists at the National Center for Radiation Research and Technology in Egypt teamed up with Al-Azhar University. They wanted to see what happens when you zap polymer nanocomposites with gamma rays and ion beams. Spoiler alert, it's awesome. So they took polyvinyl alcohol nanocomposites mixed with multi-wall carbon nanotubes and hit them with radiation. The goal? Boost electrical conductivity. And guess what? They nailed it. The conductivity shot up to an impressive 9.30 x 10⁵ SCM. That's a big deal for tech applications. Now check this out. Ion beam irradiation didn't just boost conductivity. It also improved swelling resistance, making these materials stable even in humid environments. And the microscopic analysis? It showed a uniform nanostructure that's crucial for reliable electronics. So why should you care? Well, these advancements could revolutionize multiple industries. In electronics, think better circuit boards, sensors, and even flexible displays. In medicine, how about biocompatible electrodes and smart medical devices? This tech could seriously push the boundaries of what's possible. And here's the kicker. This could be huge for Egypt's economy. Local production of advanced materials means less reliance on imports and a big boost for the high-tech industry there. So, what do you think? Could radiation tech be the key to future innovation? Let me know in the comments. This has been another deep dive into next-gen tech. If you don't like science fiction but still love cutting-edge tech, then stick around. Welcome to For Science Salah Lotfy channel. Today, we explore a fascinating study on how gamma and ion beam irradiation can transform polymeric nanocomposites. Imagine boosting electrical conductivity in materials used for electronics, energy storage, and even smart materials. A team of brilliant scientists from Egypt, including Professor Dr. Salah Lotfy, for the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Associate Professor Dr. Ali Atta, from Physics Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. And Associate Professor Dr. Eslam Abdeltwab, Physics Department, Faculty of Science, Girls Branch, Al-Azhar University, Cairo, Egypt, conducted this groundbreaking research. Published in the Journal of Applied Polymer Science, their study reveals how radiation can enhance the properties of these nanocomposites, making them more efficient and versatile. So, next time you think about radiation, remember, it's not just for superheroes, it's revolutionizing materials science. Don't forget to like, subscribe, and stay curious. Welcome back to For Science Salah Lotfy channel. Today we're diving into an exciting study on how irradiation transforms polyvinyl alcohol, or PVA, matrices combined with carbon nanotubes. We're talking gamma rays, ion beams, and some seriously cool science. Let's get into it. First up, gel content analysis. Gel content is all about how cross-linked our polymer matrix is. Think of it like the glue that holds everything together. Gamma irradiation hit a whopping 98% gel fraction, while ion beam irradiation got up to about 90%. Why the difference? Gamma rays dive deep, creating a stable matrix, whereas ion beams tweak the surface, giving us a slightly lower cross-linking density. Now, on to swelling behavior. Swelling tells us how much the matrix likes to soak up water. All samples stayed below 0.6%, showing a tight cross-linked network. But here's the twist. Ion beam-treated samples swelled a bit more than gamma-treated ones. Ion beams modify the surface, enhancing water absorption through capillary action. Add some carboxyethyl acrylate, or CEA, to the mix, and you get hydrogen bonds limiting free hydroxyl groups, keeping swelling in check. Next, structural analysis with FESEM. High-magnification images revealed some cool details. Gamma-irradiated samples had well-distributed nanotubes embedded within the matrix, while ion beam irradiation caused surface disturbances, think microholes and crystalline structures. This means ion beams tweak surface roughness and porosity, potentially boosting mechanical strength and conductivity. Let's talk EDX analysis. This technique confirmed the presence of multi-walled carbon nanotubes, or MWCNTs. We saw distinct nanotube formations with diameters between 54 and 82 nanometers. These well-dispersed nanotubes are key to enhancing electrical and mechanical properties. Lastly, FTIR spectroscopy gave us insights into chemical interactions. We saw significant spectral shifts in irradiated samples. The broad peak around 3,200–3,400 cm1, indicative of hydroxyl groups, diminished due to aldehyde interactions from glutaraldehyde cross-linking. After ion beam exposure, this peak shifted to 2950 cm1, revealing additional chemical modifications. In summary, gamma irradiation gives us higher gel content and uniform cross-linking. Ion beam irradiation introduces microstructural changes, enhancing swelling properties. FESEM and EDX confirmed successful nanotube integration, and FTIR revealed significant chemical modifications. These findings open new possibilities for advanced materials with improved mechanical, chemical, and electrical properties. Thanks for watching For Science Salah Lotfy channel. Don't forget to like, share, and subscribe for more scientific adventures. Hey everyone, welcome to For Science Salah Lotfy channel. Today we're diving into some fascinating research on polymer nanocomposites. Specifically, we're looking at how multi-walled carbon nanotubes, MWCNTs, and irradiation can supercharge the electrical conductivity of polyvinyl alcohol, or PVA. So why does this matter? Well, PVA is super versatile, but its electrical insulation properties limit its use in advanced electronics. Researchers have come up with a novel trick, cross-linking PVA with glutaraldehyde and integrating MWCNTs. The result, a conductive polymer matrix. Now let's get into the nitty-gritty. Fourier transform infrared spectroscopy, or FTIR, confirms the structural changes. We see specific peaks at 1720 cm1 and 2950 cm1 for aldehyde groups, and a broad peak at 3300 cm1 for secondary amines in the MWCNT-functionalized sample. This tells us acidyl rings and ether linkages are forming, which is crucial for enhancing the polymer network. Next, the researchers measured the direct current, DC, electrical conductivity at different voltages, from 1V to 20V. The results follow Ohm's law current increases with voltage. For plain PVA, the current is a mere 7.64 x 10^8a, add MWCNTs, and bam! The current shoots up to 3.99 x 10^4a. Functionalized MWCNTs, slight dip in current, but still impressive. Irradiation takes it up another notch. Ion beam irradiation transforms the structure, boosting current flow. Gamma irradiation smooths out defects in MWCNTs, slightly lowering current but improving overall quality. Overall, the electrical conductivity of PVA significantly improves thanks to the MWCNT networks forming continuous conductive pathways. The highest conductivity, 8.33 x 10^3 SCM, is achieved with 150 kGy gamma irradiation. Ion beam irradiation ramps it up even more. As conductivity goes up, resistance drops. Neat PVA has a resistance of 16 x 107 omega. With functionalized MWCNTs, it plummets to 2.1 x 102 omega. Gamma and ion beam irradiation reduce it further, making the material super promising for electronic applications. In summary, MWCNTs and irradiation can transform PVA from an insulator to a moderately conductive material. This opens up exciting possibilities for polymer-based electronics, sensors, and smart materials. Thanks for watching For Science Salah Lotfy channel. Don't forget to like, subscribe, and share for more cutting-edge scientific insights. We live in a world driven by electricity. It powers our homes, our devices, and even our bodies. But what if we could unlock the potential of electricity in new and innovative ways? Imagine a world with flexible electronics, self-powered medical devices, and energy storage solutions that are both efficient and sustainable. This is the promise of conductive polymers, materials that can conduct electricity while retaining the flexibility and versatility of traditional plastics. Scientists and engineers are constantly pushing the boundaries of materials science, seeking ways to enhance the electrical conductivity of polymers. One promising avenue is the use of radiation, specifically gamma and ion beam irradiation, to modify the structure and properties of these materials. This essay will delve into the fascinating world of conductive polymers, exploring how radiation can transform ordinary plastics into extraordinary conductors with the potential to revolutionize various industries. Polymers, long chains of repeating molecules, are ubiquitous in our daily lives. From plastic bags to clothing fibers, they are valued for their versatility and affordability. However, most polymers are inherently poor conductors of electricity. This is where nanotechnology comes in. By incorporating tiny particles called nanoparticles into the polymer matrix, we can create a new class of materials known as polymer nanocomposites. These nanocomposites exhibit enhanced properties compared to their constituent parts. In this context, we focus on polyvinyl alcohol, PVA, as the base polymer and carbon nanotubes, CNTs, as the conductive filler. PVA is a water-soluble polymer known for its good film-forming ability and biocompatibility, making it suitable for various applications. CNTs, on the other hand, are cylindrical structures of carbon atoms with exceptional electrical conductivity, mechanical strength, and thermal stability. By combining the flexibility of PVA with the conductivity of CNTs, we can create nanocomposites with tailored properties. However, simply mixing these materials is not enough to achieve optimal performance. The distribution and interaction between the polymer and the nanoparticles play a crucial role in determining the overall conductivity of the nanocomposite. This is where radiation treatment comes into play. To create these remarkable conductive polymers, we start with a carefully orchestrated process. Our journey begins with the preparation of the PVA solution and the dispersion of the carbon nanotubes. The PVA powder is dissolved in water, creating a viscous liquid that will act as the matrix for our nanocomposite. Meanwhile, the carbon nanotubes, in this case both pristine multi-walled carbon nanotubes, MWCNTs, and functionalized MWCNTs with amine groups, MWCNT-NH₂, are dispersed in water using sonication. Sonication, the application of high-frequency sound waves, helps to separate and evenly distribute the nanotubes within the water, preventing clumping and ensuring a homogeneous mixture. This is crucial for achieving uniform conductivity throughout the final nanocomposite film. Once both the PVA solution and the CNT dispersions are ready, they are carefully mixed. The mixture is then cast onto a substrate, like a glass plate, and left to dry. This drying process allows the water to evaporate, leaving behind a thin film of the PVA-CNT nanocomposite. This film, now containing the building blocks of conductivity, is ready for the next critical stage: radiation treatment. Gamma radiation, a high-energy form of electromagnetic radiation, is a powerful tool for modifying the properties of materials. When gamma rays interact with matter, they can knock electrons off atoms, creating ions and free radicals. These highly reactive species can then initiate various chemical reactions, leading to changes in the material's structure and properties. In the context of our PVA-CNT nanocomposites, gamma radiation plays a crucial role in enhancing conductivity. When the nanocomposite film is exposed to gamma rays, the radiation interacts with the PVA chains, causing them to cross-link. Cross-linking is the formation of chemical bonds between adjacent polymer chains, effectively creating a three-dimensional network. This cross-linking process has a profound impact on the properties of the nanocomposite. Section 5. Ion beam irradiation, a precise approach. Ion beam irradiation offers a more controlled and localized approach to modifying material properties. Unlike gamma rays, which penetrate deeply and interact broadly with matter, ion beams can be precisely focused and their penetration depth controlled. This allows for targeted modifications within the material without affecting the bulk properties. When an ion beam interacts with the PVA-CNT nanocomposite, it can cause localized heating and excitation of atoms. This can lead to the breaking and reforming of chemical bonds, effectively tailoring the structure and properties of the material at a nanoscale level. By carefully controlling the ion beam parameters such as ion type, energy, and fluence, we can fine-tune the degree of modification and achieve the desired properties in the nanocomposite. Section 6. Unlocking the secrets, analyzing the results. After treating our PVA-CNT nanocomposites with either gamma or ion beam irradiation, we need to analyze the effects of these treatments. How did the radiation change the structure of the nanocomposite? Did it achieve the desired effect of enhancing conductivity? To answer these questions, we employ a variety of characterization techniques. One crucial aspect we investigate is the cross-linking efficiency. This tells us how effectively the radiation treatment created those interchain bonds within the PVA matrix. We also look at the swelling behavior of the nanocomposite. By measuring how much the material swells in a solvent, we can infer the degree of cross-linking. A highly cross-linked network will resist swelling, while a loosely cross-linked network will absorb more solvent and swell significantly. Section 7. Cross-linking and swelling. Understanding the structure. The results of our cross-linking efficiency and swelling tests provide valuable insights into the structural changes induced by radiation. we find that both gamma and ion beam irradiation lead to increased cross-linking in the PVA-CNT nanocomposites. This is evident from the higher gel content observed after irradiation, indicating a greater proportion of cross-linked polymer. Furthermore, the swelling tests reveal a decrease in swelling ratio with increasing radiation dose. This inverse relationship confirms that higher radiation doses lead to a more tightly cross-linked network, which restricts the material's ability to absorb solvent and swell. These findings highlight the effectiveness of both gamma and ion beam irradiation in modifying the internal structure of the nanocomposite. Section 8. Surface Morphology and Conductivity. Observing the changes. The surface morphology, or the texture and topography of the nanocomposite surface, is another crucial aspect we examine. Using techniques like scanning electron microscopy, or SEM, we can visualize the surface at a nanoscale level. These images reveal how the radiation treatment affects the distribution of CNTs within the PVA matrix and any changes in surface roughness. But the ultimate test lies in measuring the electrical conductivity of the treated nanocomposites. We find that both gamma and ion beam irradiation significantly enhance the conductivity of the PVA-CNT films. This improvement can be attributed to the increased cross-linking, which creates a more rigid structure that facilitates electron movement through the CNT network. The radiation treatment may also induce changes in the CNTs themselves, further contributing to the enhanced conductivity. Section 9. Applications, from electronics to energy. The enhanced conductivity achieved through radiation treatment opens up a world of possibilities for PVA-CNT nanocomposites. These materials hold immense potential in various applications, including flexible electronics. Imagine foldable smartphones, bendable displays, and wearable sensors that conform to the contours of your body. Conductive polymers like our irradiated PVA-CNT nanocomposites can make these futuristic devices a reality. Biomedical sensors. The biocompatibility of PVA makes these nanocomposites suitable for developing implantable sensors for monitoring vital signs like glucose levels, heart rate, and brain activity. The enhanced conductivity allows for efficient signal transduction, enabling real-time health monitoring. Energy storage devices. As we transition towards renewable energy sources, the need for efficient energy storage solutions becomes paramount. Conductive polymers can be used to develop supercapacitors and batteries with high energy density and fast charging capabilities. The future of conductive polymers is bright, and radiation treatment will undoubtedly play a key role in unlocking their full potential. As research progresses, we can expect to see even more innovative applications of these remarkable materials, shaping the world around us in ways we can only imagine. Hey everyone, welcome back to the channel. Today we're diving into some seriously cool science on how radiation can supercharge polymer nanocomposites, making them perfect for advanced electronics. Now, this isn't just any study, it's a collaborative work by some brilliant minds. This is the second part of the study. Shout out to Associate Professor Dr. Ali Atta from the Physics Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. Professor Dr. Salah Lotfy, the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. And Associate Professor Dr. Eslam Abdeltwab from Physics Department, Faculty of Science, Girls Branch, Al-Azhar University, Cairo, Egypt. Their groundbreaking research was published in the Journal of Applied Polymer Science. So, what's the big deal about irradiated polymer nanocomposites? Well, these researchers looked into how hitting polymer/multi-walled carbon nanotube composites with gamma rays and ion beams changes their dielectric properties. With irradiation, these materials can store more charge and have better polarization effects. That's a game changer for electronic applications. Next, the dielectric loss, or epsilon. This is about how well the material dissipates energy. Improved dielectric loss means these composites are excellent for capacitors and sensors. And let's not forget electrical stability. Radiation makes these materials better at transporting charges, ideal for energy storage devices. In short, irradiation makes polymer nanocomposites smarter and more efficient, paving the way for next-gen electronics. If you've got questions or want to dive deeper, reach out to Professor Dr. Salah Lotfy at samaz711@yahoo.com. Don't forget to like, share, and subscribe if you enjoyed this deep dive into advanced materials. Hey there, science fans! Today we're diving into the amazing world of polymer nanocomposites. These materials are like superheroes in the world of materials science, combining the best of both worlds. Polymers, like the plastic in your water bottle, are lightweight and easy to work with, but they're not that strong. That's where nanomaterials come in. Nanomaterials are super tiny particles with amazing properties. Imagine a world with flexible phones that never break, super efficient solar panels, and even lighter airplanes. That's the promise of polymer nanocomposites. These materials are already making waves in electronics, aerospace, and even medicine. But scientists are always looking for ways to make them even better. One of the most exciting nanomaterials is the carbon nanotube. Picture a sheet of carbon atoms, rolled up into a tiny tube just a few nanometers in diameter. That's a carbon nanotube. These little tubes are incredibly strong and conduct electricity really well. However, there's a catch. They don't like to mix with polymers very well. It's like trying to mix oil and water. To solve this problem, scientists use a trick called amino-functionalization. They attach tiny molecules called amines to the surface of the carbon nanotubes. These amines act like bridges, helping the nanotubes connect with the polymer chains. This creates a much stronger and more uniform nanocomposite material. Now, let's head to the lab and see how these nanocomposites are made. We'll start with a polymer called polyvinyl alcohol, or PVA for short. PVA is a common polymer used in everything from glue to contact lenses. To make our nanocomposite, we'll mix PVA with our amino-functionalized carbon nanotubes. We'll dissolve both ingredients in a solvent and give them a good stir. Then we'll pour the mixture onto a flat surface and let the solvent evaporate. Voila! We're left with a thin film of our polymer nanocomposite. But we're not done yet. To further enhance its properties, we'll use some high-tech tools like gamma ray and ion beam irradiation. Section 4. Zapping for betterment: the effects of gamma and ion beams. Gamma rays and ion beams are like tiny bullets of energy. When they hit our nanocomposite film, they can knock some of the atoms around. This might sound destructive, but it can actually be a good thing. By carefully controlling the dose of radiation, we can create cross-links between the polymer chains and the carbon nanotubes. Think of it like weaving the materials together even tighter. This makes the nanocomposite stronger, more heat-resistant, and even better at conducting electricity. Section 5. Supercharging performance enhanced properties for advanced applications. So, what do all these improvements mean in the real world? Well, for starters, our enhanced nanocomposite could be used to make flexible electronics that are tougher and more durable. They could also lead to more efficient sensors for medical devices and environmental monitoring. And because these nanocomposites conduct electricity so well, they could even be used in next-generation batteries and supercapacitors. This means we could have smaller, more powerful, and longer-lasting energy storage devices for everything from smartphones to electric cars. The future is bright, and it's nano-powered. So, what exactly are we working with? We're using polyvinyl alcohol, or PVA, blended with multi-walled carbon nanotubes, known as MWCNTs. Imagine these nanotubes like tiny, super-strong straws in your favorite polymer cocktail. We mix PVA with 2-carboxyethyl acrylate and our nanotubes sourced from Graven Chemical Industries in Turkey. To get everything to blend nicely, we use sodium dodecyl sulfate as a surfactant. Once blended, we chemically cross-link the solution with glutaraldehyde, cast it into thin films, and dry it under vacuum for 48 hours. Voila! Our polymer nanocomposites are ready for the next step. Now let's talk radiation. To enhance our nanocomposites, we expose them to gamma rays and ion beams. For gamma irradiation, we use a 60 Co gamma source, zapping our films at 50 and 100 kGi. This strengthens the cross-linking and tweaks the surface properties. Next, ion beam irradiation. We use a cylindrical anode ion source with 4 keV ion energy and 100 UACM2 beam intensity. The films are bombarded with argon ions at fluences of 2.5 x 1018 and 3.75 x 1018 ions CM2. These treatments boost the mechanical, electrical, and thermal stability of our nanocomposites. But how do we know it works? We put our materials through the ringer with various tests. Thermal stability, checked with a Shimadzu TGA-50 system. Structural analysis confirmed with X-ray diffraction at NCRRT in Cairo, Egypt. Surface morphology, examined through scanning electron microscopy. And last but not least, electrical measurements. We use a Hioki LCR bridge to test dielectric properties and AC conductivity across a frequency range of 100 Hz to 1 MHz. The results? Significant improvements in conductivity, making these nanocomposites perfect for advanced electronics. So there you have it. Radiation technology is enhancing polymer nanocomposites, leading to more efficient and durable materials for high-tech industries. If you enjoyed this deep dive, hit that like button, share, and subscribe for Science Salah Lotfy channel. Hey there, science fans. Today, we're diving into the fascinating world of polymer nanocomposites. These incredible materials are like the superheroes of the material world, combining the flexibility of polymers with the strength and special properties of nanoparticles. Think of it like this. Imagine mixing tiny, super strong diamonds into your rubber band. You'd get a material that's both stretchy and incredibly tough. But wait, there's more. We can make these nanocomposites even more powerful with a little something called radiation. Now don't worry, we're not talking about the dangerous kind. We're talking about controlled beams of gamma rays or ions, like tiny energy bullets, that can tweak the structure of our nanocomposites at the atomic level. This radiation magic can significantly enhance their properties, making them even more useful for a wide range of applications. So, buckle up as we explore how gamma and ion beam irradiation take our polymer nanocomposites from super to super duper. We'll uncover the science behind these amazing transformations and discover how they're shaping the future of technology. Get ready for a wild ride through the world of material science. One of the coolest things about radiation treatment is how it toughens up our nanocomposites against heat. Think about a hot summer day. You wouldn't want your phone melting in your hand, right? We need our gadgets and gizmos to withstand high temperatures, and that's where thermal stability comes in. To test this superpower, scientists use a clever technique called thermogravimetric analysis, or TGA for short. Imagine a tiny scale that can measure the weight of something as it gets hotter and hotter. That's TGA in a nutshell. By carefully tracking the weight changes, we can tell how resistant a material is to heat degradation. And guess what? When we zap our nanocomposites with radiation, their TGA results show a remarkable improvement in thermal stability. They can withstand much higher temperatures before they start to break down. This means our gadgets can stay cool under pressure, literally. Now let's put on our X-ray goggles and delve deeper into the structure of these amazing materials. Just like doctors use X-rays to see inside our bodies, scientists use a technique called X-ray diffraction, or XRD, to peek into the atomic arrangement of materials. XRD works by shining X-rays at a sample and observing how they scatter. The pattern of scattered X-rays acts like a fingerprint, revealing the unique arrangement of atoms within the material. It's like piecing together a puzzle, but instead of cardboard pieces, we're dealing with atoms. When we analyze the XRD patterns of irradiated nanocomposites, we discover fascinating changes. The radiation causes the atoms to rearrange themselves, forming stronger bonds and a more tightly packed structure. This explains why irradiated nanocomposites exhibit superior mechanical strength and durability compared to their non-irradiated counterparts. To truly appreciate the magic of radiation, we need to zoom in even further and explore the microscopic world. This is where scanning electron microscopy, or SEM, comes in handy. Imagine a super-powered microscope that uses electrons instead of light to create incredibly detailed images of surfaces. That's SEM. With SEM, we can see features as small as a few nanometers. That's about 100,000 times smaller than the width of a human hair. It's like exploring a whole new universe at the nanoscale. When we compare the SEM images of irradiated and non-irradiated nanocomposites, we observe striking differences. The radiation treatment can modify the surface morphology, leading to a rougher texture or a more uniform distribution of nanoparticles. These changes can significantly influence the material's properties, such as its ability to interact with light, water, or other substances. Now let's talk about electricity. Dielectric materials are like insulators. They prevent the flow of electrical current. But they also have a hidden talent. They can store electrical energy, like tiny capacitors. Radiation treatment can significantly enhance the dielectric properties of our nanocomposites, making them even better at storing energy. This is because the radiation can create defects and introduce polar groups within the material, which act like tiny magnets for electrical charges. Improved dielectric properties are crucial for many applications, especially in the world of electronics. Imagine thinner, more powerful capacitors that can store more energy for your smartphones, laptops, and electric vehicles. That's the power of radiation-enhanced dielectric materials. Section 6. Let the current flow enhanced electrical conductivity. While some applications require materials that block electrical current, others demand the opposite, excellent conductivity. And guess what? Radiation can help us there too. By carefully controlling the type and dose of radiation, we can actually increase the electrical conductivity of certain polymer nanocomposites. This is because the radiation can create conductive pathways within the material, allowing electrons to flow more freely. This newfound conductivity opens up exciting possibilities for applications like flexible electronics, sensors, and electromagnetic shielding. Imagine bendable phones, wearable health monitors, and lightweight materials that protect sensitive electronics from interference. The future is conductive thanks to radiation. Section 7. Real-world wonders, applications in electronics and energy. The amazing properties we've discussed, enhanced thermal stability, improved mechanical strength, boosted dielectric properties, and tunable electrical conductivity, make radiation-treated polymer nanocomposites ideal candidates for a wide range of real-world applications. In the ever-evolving world of electronics, these materials are paving the way for smaller, faster, and more powerful devices. They can be used in capacitors for energy storage, as protective coatings for delicate circuits, and even as conductive inks for printed electronics. But wait, there's more. These materials are also making waves in the field of energy. They hold immense potential for developing next-generation batteries with higher capacity and faster charging times. Moreover, their unique properties make them suitable for solar cells, fuel cells, and other energy harvesting technologies. Section 8. A bright future. The potential of radiation in material science. As we continue to explore the remarkable potential of radiation in material science, we're only scratching the surface of what's possible. With further research and development, we can unlock even more incredible properties and applications for these versatile materials. Imagine self-healing materials that can repair themselves after damage, smart materials that can adapt to their environment, and even biocompatible materials for use in medical implants and drug delivery systems. The possibilities are truly limitless. By embracing the power of radiation, we're not just creating new materials, we're shaping a brighter and more sustainable future for generations to come. Section 9. Conclusion. Embracing the power of radiation for a better tomorrow. From enhancing thermal stability to boosting electrical conductivity, radiation technology has emerged as a game-changer in the world of polymer nanocomposites. By precisely controlling the interaction of radiation with matter, we can unlock hidden properties and tailor these materials for a wide range of applications, from flexible electronics to energy-efficient devices. As we continue to push the boundaries of material science, radiation technology will undoubtedly play a pivotal role in shaping our future. By embracing its power, we can create a world where innovation thrives and technology empowers us to address some of the most pressing challenges facing humanity. So let's harness the power of radiation and build a brighter tomorrow together. Hey there, science enthusiasts! Welcome back to the For Science Salah Lotfy channel. Today, we're diving into the incredible world of polymer nanocomposites and exploring some groundbreaking research that's pushing the boundaries of material science. First off, let's give a huge shout-out to the brilliant minds behind these advancements. This pioneering research was driven by Professor Dr. Salah Lotfy from the Polymer Chemistry Department at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority in Cairo, Egypt. Alongside him were Associate Professor Dr. Ali Atta from the Radiation Physics Department at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. And Associate Professor Dr. Eslam Abdeltwab from the Physics Department at Al-Azhar University's Faculty of Science, Girls Branch, in Cairo. Their teamwork has led to some truly remarkable findings. The team's research, published in the Journal of Applied Polymer Science, focuses on how controlled irradiation techniques like gamma rays and ion beams can enhance the dielectric and electrical properties of polymer nanocomposites. They synthesized films using poly-vinyl alcohol blended with multi-walled carbon nanotubes and their amino-functionalized counterparts. Through precise irradiation, they achieved improved cross-linking, enhanced thermal stability, and significantly better dielectric and electrical conductivity characteristics. These advancements open up possibilities for flexible electronics, high-frequency optical devices, and energy storage systems. Pretty amazing, right? Before we wrap up, let's take a moment to appreciate the groundbreaking work of Professor Dr. Salah Lotfy, Associate Professor Dr. Ali Atta, and Associate Professor Dr. Eslam Abdeltwab. Your contributions are truly inspiring and set a high standard for future research in this field. Thank you. And to all of you wonderful viewers, thank you for tuning in and supporting our channel. We'd love to hear your thoughts and questions about this research in the comments below. What do you think are the most exciting applications of these advanced materials? Let's get a conversation started. If you enjoyed this video, don't forget to like, share, and subscribe for more cutting-edge science updates. Until next time, keep exploring, keep questioning, and stay curious.